New on Curiosity Stream. How do you connect a 16th century potato to limitless energy production? Could Napoleon's toothpick have a direct link to a machine that predicts the future? And how can a 1700s conch shell chart a course to humans connecting their brains to the internet? James Burke's visionary series Connections returns for a new generation. Experience all new Connections. With monthly, annual, and bundled plans, find the one that works for you at curiositystream.com.
This is SpaceTime Series 23, Episode 122, for broadcast on the 16th of November 2020. Coming up on SpaceTime, more evidence linking magnetars to mysterious events called fast radio bursts, the new data release which could help explain the evolution of the Milky Way Galaxy, and a new way of discovering failed stars known as brown dwarfs. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have identified a sudden and violent outburst from a type of neutron star called a magnetar as the most likely source for those mysterious events which have baffled scientists until now, known as fast radio bursts. Fast radio bursts are massive blasts of intense energy lasting just milliseconds, but so powerful they can be detected halfway across the universe. Most are singular events, never occurring in the same place twice. That's led astronomers to think they may well be signatures for some kinds of catastrophic events such as the explosive death of a star in a supernova. But a small number have been repeaters, occurring at the same location on multiple occasions. And that's raised the possibility of more than one type of event triggering a fast radio burst. The problem is, because of their short time scale and the extreme distances involved, identifying exactly what they could be has been impossible. At least until now. On April the 28th this year, a highly magnetized neutron star known as a magnetar, located in our own galaxy and catalogued as SGR 1935 plus 2154, blasted out a sudden simultaneous mix of X-rays and radio signals never observed before. A report in the journal Nature claims this flare-up included the characteristic signature of a fast radio burst. One of the study's authors, Chris Bochenek from Caltech, says while there may still be many exciting twists in the story of fast radio bursts in the future, he thinks it's fair to say that most fast radio bursts probably originate from neutron stars known as magnetars. Neutron stars are the superdense stellar remnants of stars far more massive than the Sun, which have exploded in powerful core-collapse supernovae at the end of their lives. You see, when these really massive stars run out of nuclear fuel and their core fusion process ends, gravity takes over, causing the stars to suddenly and dramatically collapse in on themselves. They do this with so much force that they can push through a natural barrier known as electron degeneracy, allowing them to crush the subatomic particles which make up atoms, the negatively charged electrons and positively charged protons in their core, forming neutrons, and hence the star's name. But what makes a magnetar so special and different from other neutron stars is its intense magnetic field. This field can be thousands of times stronger than that in a typical neutron star. And it represents an enormous storehouse of energy which astronomers suspect powers magnetar outbursts, such as fast radio bursts. In the case of SGR 1935 plus 2154, the X-ray portion of the synchronous bursts was detected by several satellites, including NASA's WIND mission. The radio component of the burst was discovered by CHIME, the Canadian Hydrogen Intensity Mapping Experiment, a radio telescope located at the Dominion Radio Astrophysical Observatory in British Columbia. The NASA-funded Survey for Transient Astronomical Radio Emissions, or STARE-2 project, also detected the radio bursts seen by CHIME. By the time these bursts occurred, astronomers had already been monitoring their source for more than half a day. It all started late on April the 27th, when NASA's Swift Space Telescope detected a round of activity from the magnetar SGR 1935 plus 2154, which is located in the constellation Vulpecula. Now, it's flared up before, but not like this. In fact, it was the most prolific flare-up ever detected emanating from this magnetar, a sudden storm of rapid-fire X-ray bursts, each lasting less than a second. And the storm raged for hours. It was picked up at various times by NASA's Swift Space Telescope, as well as NASA's Fermi Gamma Ray Space Telescope, and NISA, NASA's Neutron Star Interior Composition Explorer X-ray Telescope, which is mounted on the International Space Station. About 13 hours after the storm subsided, when the magnetar was out of view for Swift, Fermi and NISA, one special X-ray burst suddenly erupted. The blast was seen by the European Space Agency's Integral Space Telescope mission, as well as NASA's WIND spacecraft and another spacecraft operated by the Chinese government. As this half-second-long X-ray burst flared, CHIME and STARE-2 both detected a fast radio burst lasting about 1,000th of a second. The radio burst was far brighter than anything they'd ever seen before, suggesting something very much out of the ordinary. Now, this magnetar's exact distance from Earth remains poorly established, with estimates ranging from 14,000 to 41,000 light-years. Assuming it lies at the nearer end of this range, the X-ray portion of the simultaneous bursts would have carried as much energy as the Sun produces in an entire month. Intriguingly, however, it wasn't as powerful as some of the other flares in this magnetar storm eruption. And the bursts seen by NISA and Fermi during the X-ray storm are very different in their spectral characteristics from the one associated with a fast radio burst. The authors are attributing this difference to the location of the X-ray flare on the star's surface, with a fast radio burst likely occurring at or close to the magnetic pole. And this may be the key to understanding the origin of the exceptional radio signal. The magnetar's radio burst was thousands of times brighter than any other radio emissions from any other magnetars in our galaxy. In fact, had this event occurred in another galaxy, it would have been virtually indistinguishable from some of the weaker fast radio bursts observed. Also, the radio pulse arrived during an X-ray burst, something that's never before been seen in association with a fast radio burst. Taken together, the observations strongly suggest that SGR 1935 plus 2154 produced the Milky Way's equivalent of a fast radio burst, which means that it's magnetars in other galaxies which are likely producing at least some of these fast radio burst signals. Of course, for ironclad proof of the magnetar connection, astronomers would ideally like to find a fast radio burst outside our galaxy which just happens to coincide with an X-ray burst from the same source. This combination may only be possible for nearby galaxies, which is why CHIME, STARE-2 and NASA's high-energy satellites will keep searching the skies. This report from NASA TV.
In April 2020, astronomers detected an unusually bright and powerful radio signal never before recorded in our home galaxy. The source is a magnetar, a type of compact object with the strongest magnetic fields in the cosmos. Like pulsars and neutron stars, magnetars are the crushed cores left behind when a massive star explodes, but their super strong magnetic fields put them in a class by themselves. The fields are up to 1,000 times stronger than typical neutron stars, and over 10 trillion times stronger than a refrigerator magnet. They can rip molecules apart from thousands of miles away, distort the shapes of atoms, and store enormous amounts of energy. On April 27th, the magnetar, named SGR 1935, produced a rapid-fire storm of short, powerful X-ray bursts that lasted hours. The activity, first spotted by Swift, was also monitored by NASA's Fermi Gamma Ray Space Telescope and the NISA X-ray telescope on the International Space Station, along with other space missions. As the storm wound down early on April 28th, NISA recorded some 200 X-ray bursts in just 20 minutes. Later that day, SGR 1935 fired off another X-ray burst. This time, though, it was accompanied by something new, a powerful pulse of radio waves, lasting 1,000th of a second. CHIME, a radio telescope in British Columbia, led by several Canadian universities, discovered the signal and determined it came from the vicinity of SGR 1935. Another experiment, called STARE-2, and operated by Caltech and NASA's Jet Propulsion Laboratory, saw an even brighter signal at different radio wavelengths. Since 2007, astronomers have been trying to understand the sources of powerful millisecond radio signals called fast radio bursts seen from other galaxies, magnetars have been prominent suspects. The duration and energy release of SGR 1935's radio signal is closer to fast radio bursts than any other source. For the first time, astronomers saw a magnetar in our own backyard produce a signal only previously seen in other galaxies. The discovery strengthens the case that magnetars are responsible for at least some fast radio bursts. Data from NICER and Fermi on X-ray bursts at the end of the storm showed that they differed from the one that coincided with the radio signal. This event's characteristics set it apart from the other eruptions, and further study may provide clues about how it also powered the radio burst. Radio waves from normal pulsars originate high above their surfaces. Exactly where and how, we don't know. A big eruption could launch a cloud of plasma to high enough that a radio burst could form. Never before have astronomers seen a fast radio burst so close to home. It's just one more reason to watch the skies and to keep tabs on the strongest magnets in the universe.
This is SpaceTime. Still to come, the new data release which helps explain the evolution of the Milky Way Galaxy, and a new way to detect those failed stars known as brown dwarfs. All that and more still to come on SpaceTime. Okay, let's take a break from our show for a word from our sponsor, ExpressVPN, rated #1 by TechRadar. You may be wondering why you need a virtual private network. Well, it's in the name. It's all about privacy. Do you really want big brother tech companies, hackers, governments, and who knows who else snooping in on your online activities? Now, you might not have anything to hide, but it's still really creepy, and it could be dangerous for you and those you care about. Also, how often do you run across a website and you want to get information from it, but you find out that they're geo-blocked? It's all very frustrating, and it's becoming an increasing problem. And that's where ExpressVPN can help you. ExpressVPN's a simple and efficient way to protect your online privacy. It's internet without borders from the world's leading VPN provider. So, protect your online privacy today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more. And of course, you'll find the link details in the show notes and on our website. That's tryexpressvpn.com/space. And now, it's back to our show.
You're listening to SpaceTime with Stuart Gary.
Astronomers have just released GALAH DR3, the largest set of stellar chemical data ever compiled. The findings will help scientists discover how the Milky Way has changed and evolved over cosmic timescales, the role galactic collisions have played in creating the galaxy as it appears today, and it will help determine the role elements like lithium play in stellar evolution. The Galactic Archaeology with Hermes, or GALAH survey, includes more than 30 million individual measurements covering more than 600,000 stars in our stellar neighbourhood. One of the study's authors, Sven Buda from the Australian National University and Astro 3D, the Australian Research Council's Centre for Excellence in All-Sky Astrophysics in 3 Dimensions, says the chemical information gathered by GALAH is rather like getting a stellar DNA. It can be used to tell where each star's come from, determine its age, and how it's moved across the sky, and so provide a deeper understanding of how the Milky Way itself has evolved. For example, the studies identified some 20,000 stars in our own stellar neighbourhood which don't have the same chemical composition or age as our Sun or its neighbours. Buddha says the data also shows that the Milky Way's shape changed dramatically about 8 billion years ago when our galaxy collided with another smaller galaxy. That impact caused stars from the two galaxies to mingle, and the GALAH surveys allowed astronomers to identify some of the stars from that other galaxy. GALAH makes its magic using the Anglo-Australian telescope at the Siding Spring Observatory in far western New South Wales, together with an instrument attached to it called Hermes, the high-efficiency and resolution multi-element spectrograph. It's the combination of these two highly precise instruments which have given astronomers this unprecedented view of our stellar neighbourhood. Another mystery, likely soon also to be resolved thanks to new evidence from this study, is what's known as the cosmological lithium puzzle. Together with hydrogen and helium, lithium is one of the major elements that were created out of the original Big Bang of creation 13.82 billion years ago. We know that it's destroyed in some types of stars. However, modelling aimed at estimating its abundance in the universe today has so far come up short, with the calculated total amount not matching the empirical evidence. And GALAH's Data Release 3 looks like offering a solution. It seems that a lot of the oldest stars have burned through much of the Big Bang lithium. So, current measurements for this element come out lower than the amount that was initially synthesized in the early universe. Meanwhile, stars known as evolved giants should have burned through pretty much all of their lithium by now, but a lot of them still have much more than expected, and this third GALAH data release will help astronomers discover why. Buddha says the GALAH project's previous data release, DR2, back in 2018, fueled a raft of significant discoveries regarding the evolution of the Milky Way, the existence of exoplanets, hidden star clusters, and much more.
The GALAH survey is basically, it's an acronym, and it stands for Galactic Archaeology with Hermes. And Hermes is a spectrograph that we use to observe up to 1 million stars, so 1 million nearby stars, and the aim is to figure out what kind of elements these stars are composed of, how abundant are certain elements like titanium or lithium. And the idea is that we then use this to basically understand how stars form and evolve, and how, for example, elements are created, how do stars create those elements, how potentially do they also destroy these elements, and how is this all used in a bigger context. So how does the Milky Way form and evolve? And that's something that we hope that we can analyze with the data that we collect with this survey. The Hermes instrument is a spectrograph, so it's basically observing the light of stars split into the wavelengths. So you can basically see it as a kind of an instrument that basically looks at the rainbow and basically looks at particular parts of the rainbow, particular wavelengths. And if we look at different stars, so not like the sun, but actually a lot of the other stars, we see particular absorption features. This is basically where light that's coming from the star, from the interior of the star, is hitting elements in the outer atmosphere of the stars, is absorbed, and then doesn't find a way to us anymore. And we can use these kind of absorption lines to figure out which element is how abundant.
So basically it's a rainbow with little black stripes through it, where these elements are.
Exactly. Yes, exactly. Yeah. And depending how deep these kind of features are, that tells us how many elements are there of a particular element. Yeah.
And you can work out how hot it is too by how wide these black stripes are and things like that?
Exactly. Yeah. So the physics behind all of this is rather complex. We use a lot of very sophisticated models to figure that out, but different elements are differently sensitive to the temperature of the stellar atmosphere. They're also differently sensitive to how many of the elements are actually there. And all of that we can use to constrain a lot of different things like the temperature, as you said, of the star. Exactly.
This gives you an idea of the different sort of stellar populations in our neighborhood.
Exactly, yeah. So it gives us an idea of the populations, but it also gives us an idea of which stars, especially when they're, for example, very cool or when they're very hot, how they form elements. Different stars with different temperatures, for example, tend to create elements differently. They tend to also destroy elements very differently. And for example, lithium is one of those elements which is like a very, very complex one. It's very easily destroyed. It doesn't need a high temperature to destroy this element. And we can use it as a really interesting probing of if we understand actually the stellar physics of the stars, right? Because we have models, and with these models we create, so to say, fake stars, and then we can just use the observations that we take to figure out if we are actually correct, if our models are correct.
Yeah, lithium's interesting because it's one which you'd think would be destroyed pretty easily, yet there's so much of it in the universe.
That is true, yeah. I mean, lithium is one of those few elements that was actually created right after the Big Bang in what we call the Big Bang nucleosynthesis.
Yeah, everyone talks about hydrogen and helium, but lithium and beryllium were also there, weren't they? And it's very small amounts.
Exactly, yeah. And the interesting thing is it's still very hard to measure those elements in stars. There are only a few lines that you can measure, and actually our survey is one of the first ones that really measures 100,000 up to 1 million stars and really figures out how much lithium is actually in these stars. Because that's one of the big unknowns that we had. And there has been a lot of discrepancies between what the theorists predicted and what we actually measure in stars. So there's a lot of interesting things that we can learn just by measuring lithium already. There's also other events where lithium can be created, and there's also other events where it can be destroyed. So typically you need, when I say low temperatures to destroy lithium, we're talking about 2.5 million Kelvin. That's still very, very hot. But those are temperatures that you can easily reach in the interior of the star. So there are very easy ways in the universe to destroy lithium. But yeah, it can be also created in very different environments.
You were talking about a million stars you're looking at. Are they in specific parts or just the million nearest to the Earth and Sun, or how does that work?
Yeah, so typically they're still very nearby. So we're talking about still what we call the solar neighborhood. So we don't even observe stars that are as far away as, for example, the center of the galaxy. We're still like half the distance to the galactic center. That's basically the radius that we observe within. So still rather nearby, but we can already learn a lot from these stars because they're already sampling quite a significant portion of the Milky Way. And that, as you said, helps us to figure out the different populations that make up the Milky Way.
So the distance to the center of the galaxy is about 27,000 light years. So you're going about 14,000 light years.
Exactly, yeah, exactly.
At that distance, you actually see a fair bit of evolution in the Milky Way, how it's changed over time, how different stellar populations are there. And that would be raising questions about where they originated from too, wouldn't it?
Absolutely, yeah. So we see a lot of. The interesting thing is not only the distance of the stars tells us a lot, but also these stars are typically very old. So the stars that we observe are typically several 100 million years, but typically even billions of years, sometimes 12, 13 billion years old. So very, very old compared to the age of the universe, which is like 13 point something billion years. So yeah, we can use these stars to really look back in time, so to say. We can use them as some kind of time capsule to really figure out how our galaxy evolved. And interestingly, some of the things that we see is when we look back at the oldest stars, some of them have very, very different chemical signatures as the stars that we see in the local neighborhood, for example. So there's a lot of interesting things to find about very different populations of stars, and also stars that haven't even been born in the Milky Way, but have actually been, so to say, eaten up by the Milky Way. So they have been accreted, as we say.
So this would support the idea of galactic cannibalism, that galaxies grow by eating other galaxies.
Yeah, exactly. Yeah. So we typically talk about merging events, and we see a lot of evidence that this is happening. Well, we see a lot of evidence that this has happened to the Milky Way. We still see ongoing merging events, and we also see that for a whole bunch of other galaxies in the neighborhood, so to say.
We often talk about the large and small Magellanic Clouds being slowly eaten by the Milky Way. And we do that because we can see them from where we are here in the Southern Hemisphere.
Yeah.
But of course, they aren't the only ones. There's a really interesting example, typically on the other side of the galaxy, hard to see, but its stellar trail is very visible, and that's Sagittarius Dwarf Galaxy. And it looks like that may have collided several times with the disk of the Milky Way.
Absolutely, yeah. And it's interesting because we somehow still see evidence, not only because we see Sagittarius, but we also see evidence in the movement of the stars. So that there's a lot of interesting things happening where we see some kind of a damped oscillation. So the Milky Way is basically still perturbed by this interaction with Sagittarius. So yeah. Also interesting things that we have been able to measure, not only because of the survey that we conduct, but also by a satellite that is actually measuring the movement of stars, the so-called Gaia satellite. Possibly, or most likely you've heard of that satellite
anyway. This is the European Space Agency Gaia mission, yes.
Exactly, yeah. So this is an amazing, amazing data set that helps basically, all of astronomy to really get a better understanding of the Milky Way itself and stars and their movement.
That's Dr. Sven Buda from the Australian National University in Astro 3D, the Australian Research Council's Centre of Excellence in All-Sky Astrophysics in 3 dimensions. And this is SpaceTime. I'm Stuart Gary. Still to come, a new way of discovering brown dwarfs. And later in the science report, early phase 3 trials showing a better than 90% success rate for Pfizer's new COVID-19 vaccine. All that and more coming up on SpaceTime. Astronomers have, for the first time ever, discovered a brown dwarf based purely on its radio emissions. Brown dwarfs are fascinating objects. They're often described as failed stars, celestial bodies which don't have enough mass to sustain the core hydrogen fusion process, which makes stars, like our Sun for example, shine. Because of their mass, they fit into a category between the largest planets, which have about 13 times the mass of Jupiter, and the smaller spectral type M red dwarf stars, which have about 75 to 80 times the mass of Jupiter, which equates to about 0.08 solar masses. While some brown dwarfs are born as such, pretty well big planets, others may actually start their lives as spectral type M red dwarf stars. But as they burn through their nuclear fuel supplies, they lose enough mass during their evolution to cease the core fusion process, thereby turning them from red dwarfs into brown dwarfs. This newly discovered brown dwarf, catalogued as BDRJ 1750+3809 and named Elagast, was detected about 200 light-years away by LOFAR, Europe's Low-Frequency Array Radio Telescope, and the Gemini North and NASA Infrared Radio Telescopes, both located on the summit of Mauna Kea in Hawaii. The findings, reported in the astrophysical journal Letters and on the pre-press physics website archive.org, provide both a new way to detect brown dwarfs, which would otherwise be too cold to be detected by infrared telescope surveys, and possibly also a new way to find and study rogue planets and exoplanets. One of the study's authors, Michael Liu from the University of Hawaii, says the discovery opens up a whole new way to find some of the coldest objects floating in the Sun's neighbourhood, which would otherwise simply be too faint to discover with other methods. While brown dwarfs lack the fusion reactions that keep stars like the Sun shining, they can emit light at longer radio wavelengths. The same underlying process powering these radio emissions also occur in our solar system's largest planet, Jupiter. You see, Jupiter's powerful magnetic field accelerates charged particles such as electrons, which in turn produces synchrotron radiation. In Jupiter's case, radio waves and aurorae. The fact that brown dwarfs are also radio emitters allowed the authors to develop a novel observing strategy. Radio emissions had previously been detected from a handful of cold brown dwarfs, which were originally discovered and catalogued in infrared surveys before then being observed by radio telescopes. So the authors of this study decided to flip that strategy, instead using a very sensitive radio telescope to discover cold faint radio sources and then perform follow-up infrared observations with the Mauna Kea telescopes in order to see what they are. Having found a variety of telltale radio signatures in their observations, the authors then had to distinguish potentially interesting sources from background galaxies. To do so, they searched for a special form of radio waves which were circularly polarized, a feature of light from stars, planets and brown dwarfs, but not from background galaxies. Having found a circularly polarized radio source, the authors then turned to archive imagery, as well as the Gemini North and NASA infrared telescopes, to provide the measurements needed to identify their discoveries. NASA's infrared telescope is equipped with a very sensitive infrared spectrometer called SPECS. It's been the workhorse for studying brown dwarfs for the past 20 years. The authors used SPECS to obtain a spectra from BDRJ 1750+3809, which revealed a characteristic signature of methane in its atmosphere. Methane is abundant in the atmospheres of gas giants like Jupiter and Saturn, but importantly, it's also a hallmark of the coolest brown dwarfs. The findings could also allow astronomers to measure the properties of magnetic fields generated by exoplanets and even rogue planets. Cold brown dwarfs are the closest thing to exoplanets and rogue planets that astronomers can currently detect with radio telescopes, and this discovery could be used to test theories predicting the magnetic field strength of exoplanets. And that's important because magnetic fields are an important factor in determining the atmospheric properties and the long-term evolution of exoplanets. Planets without a magnetic field don't have the shield strength to hold onto their atmospheres, which are quickly blown away by stellar winds. And that means those planets are unlikely to have the conditions to be able to support life, even if they were located in the habitable zone of their host star, an area where the temperature is not too hot and not too cold, but just right for liquid water, essential for life as we know it, to exist and pool on a planet's surface. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week. With the Science Report. US pharmaceutical giant Pfizer and its German partner BioNTech are claiming early Phase 3 trial results are showing a better than 90% success rate for the new COVID-19 vaccine BNT162. The vaccine was developed as part of US President Donald Trump's Warp Speed project to accelerate COVID-19 drug development and production. The results, which are yet to be peer-reviewed, are based on initial data from a large study of 43,538 participants, including 94 confirmed COVID-19 cases. It's an mRNA vaccine, which targets the so-called spike protein of the SARS-CoV-2 virus by presenting it to the body as mRNA, which engages the body's cells to produce the protein and then provoke an immune response. But there are issues. You'll need at least 2 doses, 3 weeks apart, for the vaccine to be effective. Also, the vaccine needs to be stored at minus 70 to 80 degrees Celsius, and it can only be kept at minus 4 degrees Celsius for 24 hours, thereby posing significant logistical challenges for mass vaccination campaigns. It's one of several leading vaccines the Australian government have invested in, securing 10 million doses. The COVID-19 coronavirus has now killed almost 1.5 million people and infected some 53 million others since first spreading out of China exactly 1 year ago. A new study has found that global warming has caused an increase in the temperature of some 99% of the world's freshwater lakes. The findings, reported in the journal Nature Climate Change, found that between 1979 and 2018, lake water temperatures globally have increased by an average of 0.13 degrees Celsius. And that's important because lakes hold more than 80% of the Earth's fresh water. The new study, which is based on satellite data, underlines the vulnerability of these inland water bodies to climate change and warns of serious future consequences for many freshwater species worldwide. The research, using the latest generation of climate projections from the Coupled Model Intercomparison Project, warns that the rate of climate change is expected to accelerate during the current century, with potentially serious consequences for freshwater species. A new study claims people who be themselves on Facebook tend to report a better sense of well-being than those with a Facebook filter. The findings, reported in the journal Nature Communications, are based on data looking at the Big 5 personality traits, a common model for measuring personalities, and compared that to what a computer model believed their personality to be like, based on the language they used and their status updates. The authors found there was a correlation between authentic self-expression and higher levels of life satisfaction. Additionally, a separate study asked participants to post a more authentic version of themselves on Facebook, and they also reported a higher level of well-being than those who didn't. Data from activity trackers worn by 100,000 people in the UK show that it's not just how much you exercise, but also the intensity that matters when it comes to lowering your chances of early death. Researchers found that by simply increasing your energy use by the equivalent of adding an extra 2-minute brisk-paced walk on top of a more leisurely 35-minute stroll a day could lower your risk of early death by 21%. But if you don't have the extra time, you can simply pick up the pace, as they also found that the energy used from converting a 12-minute stroll into a brisk 7-minute walk each day could also lower the risk of early death by 30%. The findings, reported in the journal Nature Medicine, is the first study to show that intensity really does play a role in the link between physical activity and death, over and above the total volume of activity. A new study claims most anti-vaxxers believe they're health literate and are pro-science. The findings, by researchers from Melbourne's La Trobe University, examined why members from the vaccine refusal movement in Australia consider themselves a science advocacy group. However, Tim Mendham from Australian Skeptics points out questions remain about how well they really understand the science they're basing their beliefs on.
This was a study done by La Trobe University researchers who surveyed a number of vaccine refusers who obviously did not want to use vaccines because for various reasons, conspiracies, etc. What they found was that those particular people regarded themselves as being quite scientifically literate, and that their refusal was based on firm information, distinct sort of beliefs, etc., and that the mainstream vaccine movement was dishonest and compromised. The interesting thing is, of course, is that probably applies to anyone who has any belief, that they have done their due diligence, that they are right in what they believe, that they are literate as far as the evidence goes, etc. What this study didn't do was actually look at how accurate the information they believe is. They were basically looking at, the self-image of the people who refuse vaccines, right? It's an interesting study, but it's not particularly surprising, because you'd say anyone who follows a political party seriously, rather than just because their parents voted for the party, anyone who's looked at the party, looked at the policies, etc., would regard themselves as fairly politically literate, and to a certain extent economically, socially, etc., literate as well, even if they're right or wrong. So suggesting that people who refuse vaccines are scientifically literate is not the issue. They believe they are. And the answer is, of course, they would, wouldn't they?
And that's actually the key word, belief. I've found it's easy to argue facts against someone who wants to hear facts, but to try and argue against a belief is almost impossible.
It is. It is almost impossible. I mean, these people sort of say they are scientifically literate, so at least there's an in that you have there to look at the science and to understand how well-founded their science is as opposed to alternative science. I hate to say alternative facts. Therefore, if they regard themselves that seriously, right, rather than a belief but as a well-founded philosophy, then there might be some ways to talk to people to disabuse them of their beliefs, to certainly present sort of fact-based information rather than just you have studied what agrees with your opinion. The echo chamber idea, where someone just only goes to the same websites, etc., which tells them what they already know or believe. So they're not looking at any scientific alternatives, which encourages them to believe they are doing the right thing.
That echo chamber is comfortable.
A lot of us do it. Most of us do it in one way or another, whether it's sort of what car you prefer or what films you find good or what books you follow or what religion you follow or what political party you might follow. How many people actually listen to the opposition and then sit down and dispassionately make up their mind? So these researchers have found out by doing their research, and they've done it sort of properly for what it is, but it's basically you tell me what you think and that's what I will summarise. And to me, it's sort of interesting, it's not surprising, and it certainly doesn't say, is what you believe accurate?
Yeah, would it be nice to include in that scope how accurately they actually understand the science they think they understand?
That's exactly right. That's exactly right. So you just do a little bit of, you do a questionnaire, are you scientifically literate, have you done your research, etc., and then throw in a few curly questions about, if you've done your research, what is your understanding of this.
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.